Hello class, so today is going to be a completely new section. We're looking at polynomials, and so this will be 60-1. We're going to describe a polynomial function. So today we're going to verify if a function is a polynomial. We're going to describe a polynomial, like the degree or the leading coefficient, etc. of it. And then we're going to determine the end behavior of a function. Now here's the definition of a polynomial. Now just know that we've kind of already taken a look at polynomials before. We took a look at constants like y equals 5, linear equations, y equals 2x plus 1, and quadratic equations, the basic one, y equals x squared. Now all of those are polynomials, and they belong to this larger group of possible polynomials. Now this definition here is basically the definition of a polynomial. Now there are a few qualities about this, and we're going to take a look at those very shortly. Now with our polynomial function that we have here, know that these coefficients, a sub 0, a sub 1, a sub n, so these are all coefficients. All of these coefficients, they're real numbers. They're not going to be imaginary. You won't see any i's. They're not going to see any complex numbers like that, okay? Then my degree n is going to be greater than or equal to 1, and it is a natural number. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, etc. Also, the domain of all polynomial functions is negative infinity to positive infinity. Now that's really important, because if we find any contradictions to these, we can then come back to that and say, well, that function is not a polynomial because it contradicted these statements we have above. Now, even though many elements about this definition can be frightening, it's best to kind of take a look at this as an example. So if I had this 4x to the fifth minus 3x squared plus 2x minus 5, I can rewrite the formula as this. Notice I didn't have an x to the fourth or an x to the third, so I say 0x to the fourth, 0x to the third. I do have a negative 3. That goes there. So just know that we do have those, and we will have to continue to use those. But now comparing it to the definition, I can say things like my a sub n, that's 4. X to the n power, my n is going to be 5. Now this says n minus 1. Well, 5 minus 1 is 4. x squared, my a sub 2 is going to be negative 3. My a sub 1 is going to be 2x, and then my constant a sub 0 is going to be negative 5. Now it may seem weird, it's like, why am I writing these n's or n minus 1? These are just locators. That is just so I'm saying that this n is referring to this power here. This would be n minus 1, so if this was a 5, this would be then a 4. Well, this would say a sub 4, and I'd say that my a sub 4 is the leading coefficient here. And so this is just terminology that allows us to locate the various elements of our polynomial. So we're going to spend some time determining if the following are actually polynomials here. So this first one here, it says 4 plus x cubed over x. Well, I can't divide by 0. If I divide by 0, I get an undefined value, so it can't be a polynomial, because we said that the domain of a polynomial has to be negative infinity to positive infinity. For this next one, it's the same thing. If I divide by x here, I'm going to get something over 0, in this case 0 over 0. That's also no, because my domain, it contradicts it. Now we're thinking, oh, we're dividing by x's. Therefore, if I'm dividing by an x, it must not be a polynomial. Well, if I set this equal to 0 and try and solve for it, x squared plus 4 equals 0. Well, minus 4 on both sides. I get x squared equals negative 4. Square root, I get x equals plus or minus 2i. Well, that's an imaginary value, so there's no real solution for that. So there's no contradiction to my domain, which in turn will actually make it into a polynomial. For this next one here, if I rewrite this, I can rewrite that as x to the 1/3. Now if I do that, this right here, we said my n has to be greater than or equal to 1 and is a natural number. Well, 1/3 isn't a natural number. And so because 1/3 isn't a natural number, or it's not greater than or equal to 1, it can't be a polynomial. For this one right here, this is an absolute value. It's like a completely different category of function, and so it can't be even a polynomial. And equals to 0, we said that we can have a polynomial function equaling 0, and so it is going to be a polynomial. Now, when we're trying to name a polynomial, right, this is another way to describe it, we call the different elements of that polynomial different names. So, for example, we would say that the natural number n of a polynomial, we call that the degree. So this value here, we call that the degree of the polynomial. Now, if we clump these values together, this a sub n x to the n, we call that the leading term of our polynomial. Now that number in front there, we call that the leading coefficient. Now to help us remember it, leading, right? Lead, when you lead, you're in front. So it's the term that's in front. It's the coefficient that's in front. So that kind of helps us understand what those elements are. And the real number a sub 0, we call that the constant term. So this right here, this is our constant term of the polynomial. And then we also say that if our function equals a sub 0, we say it has a degree of 0. But if our f of x equals 0, we say it has no degree. Now it's kind of similar, but there's specific instances as why we should be more specific in that sense. And those examples actually kind of go into it a little bit more once you go into calculus. So, all right, so the next part, it's asking us find the degree, leading term, leading coefficient, and the constant term of the polynomial functions. So my degree, right, we said it's the highest power, so that's going to be 5. The leading term, that's going to be our leading term there, so that's going to be 4x to the 5th. Our leading coefficient, that's going to be the value that's in front of our leading term, so that's 4. And our constant number that doesn't have a variable by it, that's going to be -5. Now looking at this one, our first thing, we're thinking, oh, this is our leading term, but we have to rewrite it. Okay, they should always be expressed in descending order because your degree is your highest power, and your highest power should be written first. And so because that's 3, that's going to be 3. Now my leading term, this value right here is my leading term, and so I have x to the 3rd. My leading coefficient, that's going to be the number in front, and so that's going to be a 1. My constant, there is no number by itself, so that's going to be 0. Now diving further, this one we're going to have to break apart. This is going to become -1/5 x and plus 4/5, right? We can break that 5 into both of these. So then my degree is going to be 1 because that's the highest exponent I have there. My leading term is going to be -1/5 x. My leading coefficient is just going to be that -1/5, and the constant is going to be 4/5. Now d, what do we do with d here, right? It looks like a mess. Now the trick here is if I go to a different example, let's say if I had 2x plus 1 times x minus 3, and I multiply these, those first two terms that I multiply together, that's my leading term. These last two numbers that I multiply together, if I were to distribute or FOIL that, that's going to be -3. That's going to be my constant. Now you can carry out that same pattern to as many of these polynomials that we're multiplying together. So if I take this is 2x minus 1 times 2x minus 1 times 2x minus 1. There's 3 of them. I need to sit there and I need to multiply all of these together. 2x times 2x times 2x times x times 3x. And so that's going to give me 24, and I have x to the 5th. Now my degree, how many x's do I have? 1, 2, 3, 4, 5. I have 5 x's, so that's why my degree is going to be 5. Now my leading coefficient, that's going to be the value that's in front there. Now to find my constant, we multiply these values together. Now if you go through and you multiply that, -1 and -1 is +1 times -1 is -1 times -2 is +2. +2 times +2 is +4. And so that's how we would go ahead. And now I just suggest that we kind of memorize that pattern, right? The leading coefficient, as I multiplied all of the leading terms. The constants, I multiplied all of the constants together, because we're going to need this pattern in the future as we go through and dive into polynomials even more. Now the next thing we're going to talk about, and the last thing, is going to be end behavior. Now the end behavior of a function is a way to describe what is happening to the function, my y values, as my x values approach the quote-unquote ends of my x-axis. That is, what happens to y as x becomes small without bound, and what happens to y as x becomes large. So for this first example, if I said f of x equals x squared, as x goes to -infinity, what I'm saying is I'm basically substituting that x is getting -100, -1,000, -10,000, etc., etc. Now if I do that and I actually plug them in, notice my values are getting huge. And so to describe my end behavior, I would write as x goes to -infinity, my y is also getting really big. Now applying that same concept to the other side, as x goes to +infinity, my y is also getting really, really large as well. Because if I plug in +100, okay, it's still going to give me 10,000, so my y's are getting large. So now we're going to take a look at this visually. Now I'm going to take these two slides, I'm going to put them together for us in a moment, but we're just going to kind of dissect the elements here. The first is when n is even. Now when n is even here, so ax to the n power, basically they're both going to either go up at the same time or they're both going to go down. Okay, the ends of the graph are either both going to go up and they're both going to go down. Now if my leading coefficient is positive, they're both going to go up. If my leading coefficient is negative, they're both going to go down. Now when my degree is odd, they're going to have this power. It's almost like a cubic, right? Like x to the third power. It kind of has that shape there. Now just to kind of clarify, this dotted line that we see here, this is just saying I have no idea what's going on between, but I do know for certain, because of the end behavior, these values are going to do this. I don't know what's in between, but I do know this portion here. So the idea of, with this cubic function, when my a is positive or my leading coefficient is positive, it matches like that of a cubic, and then when it's negative, remember there's a reflection, so this gets reflected down, which is why it's there. This gets reflected up, which is why it's going that way. So it kind of helps us. Now taking both of those and putting them together, this is kind of like what our end behavior is going to look like. Now we're looking at two things. Remember, we're looking at, is our degree even or odd, and is my leading coefficient positive or negative? If my degree is even and my leading coefficient is positive, we kind of combine them together. This is the shape it's going to look like. If my degree was odd and my leading coefficient was negative, where these two values intersect, this is what my end behavior would look like. Now I can go ahead and write in, as x goes to -infinity, my y, it's going up, so that's going to go to +infinity. As x goes to +infinity, what is my y doing? That's also going up, so my y is going to +infinity. For this one, as x goes to -infinity, and I have x goes to +infinity, well, as x goes to -infinity, my y is going to -infinity. And then my y, as x goes to +infinity, my y is also going to -infinity. So for this one here, we have x going to -infinity and x goes to +infinity. So as my x goes to -infinity, my y is also going to -infinity. And then as my x goes to +infinity, so does my y. And now my next function, as my x goes to -infinity, x goes to +infinity. As x goes to -infinity, my y goes to positive infinity. And as my x goes to positive infinity, my y goes to negative infinity. So those will be my end behaviors kind of describing those. So now let's kind of practice putting these together. Example number 3 says sketch the end behavior of the following. So remember, I said we have to look at two different things. We look at first the degree. Well, my degree is even. Then the leading coefficient, is it positive or negative? And it's positive. So therefore, using that chart, right, where it's even and positive, where they both coincide, we're going to a shape that looks like that. Now remember, I have no idea what's going on here. I just know my ends of the graph are doing that. Once again, for this one, my degree, odd. My leading coefficient, negative. So therefore, using that same chart where they cross, you're going to have this image here. My degree, odd. Leading coefficient, positive. So it's going to have that image. My degree, even. Leading coefficient, negative. And so it's going to have that image there. So this does conclude our lesson. If you guys have any other questions, please leave them in the comments.